Okay, we're talking about titrations today and a little bit about acid-base. All right, so you've probably seen titrations before. You've seen how we can sometimes discover things about a solution by reacting it completely with another solution. So that other solution that we use, that is a standard solution. If you have a standard solution, you know its molarity. And knowing its molarity and reacting it until all of this other solution reacts, as evidenced by a color change generally, allows you to know either the molarity of the substance or the number of moles or grams of that acid or base in that substance. So, in fact, you know, oftentimes you have that color change, and so an indicator will allow you to know that you have reached that equivalence point when all of your base is completely reacted with the acid added, or all of the acid is completely reacted with the base being added. Now, in some calculations, particularly you'll find in your homework, you will need to find, say, the molarity of some solution being tested. So what you might do is consider that you're adding a certain number of liters of known molarity acid or base. But presuming we're adding acid, you know the number of moles of acid. And because we add just enough acid to react with all the base at the bottom, then we can convert from moles of acid to moles of base. And so, yeah, you can do that mole-to-mole conversion if you have reached precisely the equivalence point. And so knowing the number of moles of base and perhaps the number of liters of base solution, you might find the number, or the moles per liter, or the molarity of that base solution. Now, how do we get these standard solutions? Well, you might think that the solution that I make up, say I make up a 0.8 molar HCl solution, is precisely 0.800 molar HCl solution. But in fact, it's not unless I actually test it. This is the case for acid and particularly with base, being that the base that we add, sodium hydroxide, often it absorbs water from the air. It's hygroscopic, and so even though I might add a certain number of grams of sodium hydroxide to water, in fact I added less sodium hydroxide than I had intended. But here we have a question. Instead of determining the molarity of a standard sodium hydroxide solution, which you will probably do a homework problem on by testing the amount of KHP, potassium hydrogen phthalate, needed, in this problem the question is, what is the molarity of an HCl solution if 13.2 milliliters of that solution are required to react with 0.256 grams of sodium carbonate? And so if you use an ultra-pure sodium carbonate solution which has been kept away from water so it hasn't absorbed that water, then you can place that known mass of sodium carbonate then in water and dissolve it and create a solution. And then knowing then, therefore, the number of grams and then moles of sodium carbonate and reacting the hydrochloric acid just enough of it to reach the equivalence point, you can know the moles of hydrochloric acid added. And if you know how many liters of hydrochloric acid were added as well, you know the moles in liters, you'll know the molarity of the hydrochloric acid. So essentially, we will often standardize a solution of unknown molarity by reacting it with a solution of known molarity, or at least known number of grams of acid or base. So we want to solve this problem, go from grams of sodium carbonate into ultimately the molarity of that hydrochloric acid solution. So you've seen this before. To go from one type of compound into another, you got to go into the land of the mole. And so go ahead and convert from grams of sodium carbonate into moles of hydrochloric acid. You know that there's 105.97 grams of sodium carbonate per mole, presuming that you have very, very, very dry, aka very anhydrous, without water sodium carbonate. And then you can go from moles of one thing into moles of another. Oh my gosh, this is a stoichiometry problem. Can you solve these stoichiometry problems just saying, oh, 1 and 1? No. In fact, in order to do a stoichiometry problem, you must at least consider the balanced chemical equation. So let's write that one out now. And this one actually is kind of special, so I want you to pay attention. We're reacting hydrochloric acid with sodium carbonate. So what happens when you react an acid with a base? Well, you know that when you react an acid with a base, you'll generally have, in a neutralization reaction, you'll get a salt and water. But this is kind of a special case. You see, those hydrogens switch places with the sodium so that you do get sodium chloride, and you get hydrogens stuck to carbonate. You get, let's see, hydrogens H plus and carbonate is CO3 2 minus. You need 2 hydrogens per carbonate. You'll get H2CO3, but that's not water, is it? But hold on. You see, this is carbonic acid and is quite unstable in solution. And so what it actually will do is break down very quickly into, yeah, that water and a carbon dioxide molecule, which is gaseous. So in fact, what happens when we react in any acid with a carbonate base, it has CO3 in it, either sodium carbonate or baking soda. When we react an acid with a carbonate, we get a salt, water, and carbon dioxide gas. So what would it look like as you are reacting this carbonate in your solution with hydrochloric acid? As you drop in the acid, what will you see happen? Carbon dioxide bubbles will be released. And then eventually, when you've completed the equivalence or reached the equivalence point, then you'll get color change. All right, so let's go ahead and now balance this equation. Let's see. Per carbonate, we need 2 hydrogens per carbonate. So we'll put a 2 there. And so there's going to be 2 chlorines. I have only 1 chlorine here. Put a 2. Now I have 2 sodiums. I have 2 sodiums. I had 1 carbonate. I have 1 carbonate, which turned into CO2. All right. So now we know the mole-mole ratio. It's not 1 to 1. It's 2 to 1. And so now we can find the number of moles of HCl. It's 0.00483 moles of HCl. Now we can find the molarity of that hydrochloric acid solution. We had those 0.00483 moles. And how many liters of HCl solution do we have? Well, we added 13.2 mils, so we added 0.0132 liters of solution, and so the molarity then is 0.366 molar. So you definitely need to be able to do these 2 things. Just a good old standard, using a standard solution to determine something about an unknown, but also you need to be able to learn how to standardize a solution to determine what is the molarity of that solution, either using a base to standardize an acid like sodium carbonate with an acid, or using an acid like potassium hydrogen phthalate to standardize a base. All right, thanks for watching, guys.